Let's take a look at ethene. So I'm going to represent it like this. Like so. So what I've done was I've simply taken it drawn like this. And if I draw it like that, that means the whole molecule is in the plane. Every carbon, these two carbons are sp2 hybridized, so that makes the molecule flat, just like my hand touching the glass. Okay? And so what's the difference between this representation and this one? I simply take this molecule, which is being represented by my hand, and just rotating at 90 degrees. And so those two hydrogens right there are sticking out at me. So I can represent it like that. Okay. So we're going to use valence bond theory here to draw this guy. Now the same principles apply. What is the hybridization state for those two carbons? We see that they're sp2. And so what does the ground state of carbon look like? It's kind of the same thing as before. We have ourselves a 2s orbital and our 2p. It looks just the same. But now we have to hybridize it in a different way. We need to hybridize it into a sp2. So that means we're going to take 1s and 2p's. So I can look at it this way. I'm going to take those right there and hybridize those three orbitals to the same energy level. All right, 1, 2, 3. But this one right here, I'm not going to hybridize. I'm going to just leave it alone. And so what I have are these three right here are sp2. And this one that was left alone is a p orbital. And we fill in the electrons just like that. So that's showing us here that the carbon, let's talk about this carbon, it has 3 electrons in sp2 hybridized orbitals and 1 electron in a p orbital. All right? So this carbon is sp2 hybridized. That means that if I take that carbon, all right, and draw the carbon here, it's going to have 3 orbitals in the same in the same plane, because it's sp2, so it's flat. So it's going to have 1 sp2 hybridized orbital there, 1 there, and 1 there. So I'm trying to represent this orbital as the wedge, this one as the dash, and then this bond right there. All right? And so those are the sp2 hybridized orbitals. They're all in the same plane. All right? But now, the way I'm looking at this molecule, it looks like this. Okay? So these orbitals right here are all in the same plane. So in the same plane of my hand. Okay? Now we have a p orbital. Now what do the p orbitals look like? Well, those are going to be perpendicular. And those have phases. So this p orbital that I'm drawing is not in the same plane as those 3 sp2 hybridized orbitals. It's perpendicular. So if my hand is representing the 3 blue orbitals all in the same plane, the p orbital is above and below my hand. All right? Now, it's showing us here that we have 3 electrons in the sp2s, like that. And we have 1 electron in the p. All right? Now, this carbon here, it kind of looks like they're bonds, but they're actually not. Let's get rid of that. So we have hydrogens, and we know the hydrogens are going to be 1s orbitals, each with 1 electron each. How many hydrogens do we have? 1, 2, 3, 4. So times 4. So these two hydrogens right here are going to bond with these sp2 hybridized orbitals with a 1s with a sp2. And there it is. So those two hydrogens are represented by those two. Now we see that this carbon right here is bonded to another carbon. So let's draw ourselves another carbon right here. And that carbon is that carbon. It also is sp2 hybridized. So let's backtrack for 1 second. These 4 electrons have now been accounted for. They're all in our structure. Now this carbon over here also has 4 electrons, and I'll represent those with a different color. All right. So this carbon also is what? sp2 hybridized. So it's going to have 1 over there, 1 over there. Do you see? That's a dash. So I'm kind of representing wedge, wedge in the same orientation here. And then I have another sp2 hybridized orbital there. Notice how this orbital here is smaller than that one. That's not by design, that's just complete accident. The sizes of these two orbitals are going to be the same. And what does this carbon have? It also has a p orbital. That is perpendicular. All right, just like so. And what comes with this carbon here? Well, it has an electron in the p, and then 3 in the sp2. Do you see how we've accounted for all 4 of these? 1, 2, 3, 4. And so let's finish up our hydrogens. There's our 2 hydrogens right there. Now this bond right here is going to be called a sigma bond. So that one right there is our sigma bond. And I can represent that sigma bond with the green. Okay. But then what is this blue bond right here? That is the pi bond. And where's the pi bond happening? Well, it's going to be the interaction between these orbitals right here. So I'm going to actually take this guy and change its spin state. Okay. So now you're going to have overlap that way. And so the pi orbitals, or sorry, the p orbitals, when they overlap and interact with one another, above and below this plane. So we have a plane right here through the carbons. Okay. These two sp2 hybridized orbitals are in that plane. They're head-to-head overlap. Okay. They're within that plane. But then the pi or the p orbitals are interacting above and below that plane. Okay. Or it's not plane, sorry, I'm using the wrong word. This axis. So we have this axis right here, and these 2 orbitals are interacting head-to-head on that axis. Okay. But the p orbitals are above and below that axis. And when it's above and below that axis, that's going to be the pi bond. So this blue one right there is going to be the pi bond. And so that's how we have our double bond right there. So one is from a sigma, head-to-head overlap, and then one is a pi above and below that axis. And this is the reason why there is no free rotation around a double-double bond. Is because if you rotated around that double bond, you would disrupt the interaction between these two p orbitals. Because if you twist this carbon, that interaction between this orbital and that will be gone. And so you would destroy that double bond character. And that does not happen. Okay? So that's sp2 hybridized. So let's take a look at, so if we label everything here, okay, what's going on? Let's do a quick labeling here. So these orbitals are sp2, 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 sp2. And, okay. And then those are 1s's. The hydrogens are 1s's. And then what's the interaction between these guys? That is a 2p and a 2p. And sometimes I just say, hey, that's the p orbital, but what energy level is that p orbital? We see that it came from a 2. So we could say that's a 2p. Okay? Perfect. Let's take a look at another molecule that's going to be really prevalent in biochemistry. Okay? Let's take a look at formaldehyde. What if I draw it like this? Now, what's the hybridization state of that oxygen and the carbon? It's sp2 hybridized. So it's flat. So I'm going to represent that molecule with my hand on the glass. And I'm just going to take it and rotate it 90 degrees. And when I take that and rotate it 90 degrees, I'm going to get something that looks like this. Okay. Now this oxygen atom right here, we see that it has to have 2 lone pairs in order to be neutral. So we want to do valence bond theory here to see how all the orbitals interact for this molecule. Now, I've already shown you the hybridization state of carbon. So I'm just going to represent this carbon right here like this. So we have our sp2 right there. And then our 2p, and so our electrons look like that. Okay. But oxygen, I'll draw it over here. Same concept here. There's our 2p and our 2s. But how many valence electrons does oxygen have? 1, 2, 3, 4, 5, 6 valence electrons. Okay. So with 6 valence electrons, we have to hybridize that oxygen. So this represents oxygen. We're going to hybridize it to sp2. So that means we're going to have 2 sp2 orbitals right there, and one of them was not touched. So we just took those right there and hybridized them, and we left this guy alone. So there's our 2p. And you can't see it. So that's our 2p right there, okay? And so the electrons there going to look like this. So 1, 2, 3, 4, 5, 6. Okay? So I'm going to redraw that over here to make it look a little bit nicer. And that is for, the blue is for the oxygen atom. The green is for the carbon atom. Okay. And we've already, then we have what? We have 2 hydrogens. Okay. And so we have our 1s. And those, I'm just going to actually just do 1, say that's times 2. Okay. So there's all our electrons. Now we can put this molecule together. All right, taking a close look. So we have our carbon atom right here. The carbon atom is what? sp2 hybridized. So that means it's going to have a sp2 hybridized bond like that, and one over there, and one over there. So these three orbitals that I've drawn, I'm representing those two as those wedge and dash, and then the sigma bond with that. And I see within that orbital there, we have green, green, and green. So I've accounted for that one, and that one. I know this is sp2 hybridized, so that means we have, if it's sp2, then we have a perpendicular p orbital right there. And the green orbital electron there is now accounted for. Now we have an oxygen atom right here. What type of orbitals does the oxygen have? sp2 and a p. So it's going to have this kind of the same thing as the carbon. We're going to have a sp like this. I once again drew that sp2 orbital larger than that one. That's not the case in reality here. So we have, now what's interesting here is when we look at the hybridized here, we see that we have one electron in the p orbital. So the p orbital right here, let's make sure we have our phases. So that's a blue electron, that's in the p, so I'll put that there. Now, we have to form a sigma bond between the carbon and the oxygen. And so how do we form a sigma bond? Well, we need an orbital on the oxygen atom that has one electron in it. There it is. So this electron right here is going to be right there. Trying to draw an electron there. Now I've just blurred it all together. Can't see it very well, can you? So this electron, I just put right there. So I've accounted for it. So there's our sigma bond, and we represent that with the Greek symbol sigma. There's our sigma bond. Right there. So now, I've already accounted for that electron, which is there. We have one electron in the p, so I've accounted for that one. So what goes in here? What do you think that is? 2 electrons in the same orbital? That's the lone pair. So I counted for those two, and I'm showing them with dots, but let's be consistent here. So those 2 electrons would be like that. There's the lone pair. That one is that lone pair, and then this lone pair would be that lone pair right there. All right. And then to finish this out, what do we have? We have our hydrogens coming to us with a 1s orbital. All right. And so let's see here. So this right here, above and below that axis, that's going to be our pi bonds. So we can represent our pi bond here with a orange, and then our sigma bond right here we can represent in blue, like that. All right. So we've accounted for that one as well. So we've accounted for all the electrons and all the bonding. So when we go through and label this, that's a 1s, 1s, sp2, sp2, 2p, 2p, sp2, sp2, and These lone pairs right here, what orbitals are those in? Right there. And those are sp2 hybridized orbitals. Pretty slick. So I have one more that I want to go over, and that is with the sp hybridized orbitals, or sp hybridized carbons.